What am I doing?
Okay, starting recording. Oops. All right, my son is on spring break, so you may hear him shouting in the background.
2 whole weeks of spring break. Hey,
2
very
weeks.
wonderful,
Yeah.
isn't it?
Yeah, we don't get any spring break.
Yeah, we don't get that.
That's when we usually catch up on teaching and grading and.
Yeah, not anymore.
No. Okay, so last week we did some examples with deriving conjugate distributions, the posterior distribution of the parameters given the data when we have specific combinations of likelihoods and priors that allow us to actually analytically derive what the posterior distribution is. And then we took that posterior distribution and we coded it into our first Mcmc sampler. And when we did that, we were able to sample directly from the posterior distribution using Gibbs sampling. So Gibbs sampling is what you can use when you have conjugate distributions. You get to sample directly from the posterior distribution because you know what that form is. And we worked up to a 2-parameter model that was a simple linear regression model with an intercept and a variance. And we coded it in for sampling first the intercept. And then once we sampled the intercept, we treated that value as fixed. And then we sampled the variance. Okay, now we're going to talk more about why this works and how this works. So let's start off here. Before we go into the details, let's just take a step back and talk about what we're doing in the first place. I've showed this slide a few times now and what this course is about. It's about models and observations, where the other scientific endeavors looking at current concept theory and questions help us develop our models and collect data. And then once we have those models that specify our system in hierarchical modeling, that's usually in terms of a data model, a process model, and a parameter model, then we can write those models out and fit those to observations, and making inference on those model parameters provides new insight qualified by uncertainty in our model parameters. So uncertainty is a big part of this course, and we treat uncertainty as a probability distribution in our parameters. Okay, we talked about the rules of probability and conditioning and independence. We've used that quite a bit. Law of total probability and factor and joint probabilities allows us to get to Bayes' theorem in the first place. We've talked a lot about distribution theory, things like the support of certain distributions and matching the support of our data to those distributions. And now we're going to talk about Markov chain Monte Carlo and how we actually estimate Bayesian models. Here is a schematic of the entire Bayesian method where we start off with good experimental design when possible. So again, if we can develop an experiment where we alter one parameter or one variable at a time, that gives us the strongest inference. So that allows us to move the pace of science rapidly. However, it's not always practical to do that, and in ecology is one area where we often have observational data, and we want to gain some information from this observational data instead of experimental data. And when we do that, we often have to move away from a design-based approach with experimental design to a model-based approach. So we develop models that approximate reality and are hopefully tell us something useful about the system we're interested in. And then accumulation of knowledge will be through repeated studies on this. We can't say definitively from one experiment when we have one observational study what is driving the system, but it provides information for further investigation, and through repeated observation, we can say something about the system. All right, and then now we're going to be talking about model implementation. We talked about this word full conditional distributions last time, where we have each parameter of our model given everything else. So we need to figure out what the full conditional distributions are of our unknown parameters, our unknown quantities. And then we can write an MCMC sampling algorithm for that. Alternatively, we could write code for MCMC software, like in JAGS or Stan or Nimble or Winbugs. Then from there, we did this. We showed this in practice last Wednesday, where we implement MCMC on simulated data to make sure we can actually recover the true values that we chose to simulate the data. And we saw that after some troubleshooting, debugging, we were able to get our MCMC algorithm to recover exactly what those true values were. And then once we know our MCMC algorithm's working on simulated data where we can recover, I use that word recover, the true parameters, then we can implement it on real data and make inference from that. After we make inference, we do have to make sure our model does approximate reality. So we can write any kind of model we want and fit it to the data. The question is, if we were to use the model that we actually fit to our data to simulate new data, does that simulated data look like the real data? If our simulated data from the model we developed doesn't look like the real data, then it's probably not a very good model. And this is one of the current areas that I stress in reviews and other things like that of implementation of Bayesian methods is this last step. And we'll talk about this much more in a lecture dedicated to model checking. But right now we're on model implementation and writing MCMC sampling algorithms and why MCMC works. All right, so the MCMC algorithm and why MCMC. So we'll talk about that today. We'll provide some intuition about how it works for a single parameter model, and then we'll talk about multiple parameter models where we talk about full conditional distributions. Gibbs sampling is when we know exactly what the posterior distribution looks like. That's when we have conjugate priors. When we can't use Gibbs sampling and we can't write out the posterior distributions or the full conditional distributions of each parameter like we did last week, then we're going to have to use something called a Metropolis algorithm or a Metropolis-Hastings algorithm. And we'll talk about that today as well. All right, so learning outcomes for this lecture or the next two lectures, we want to first develop a big picture understanding of how MCMC allows us to approximate the marginal posterior distributions of parameters and latent quantities. We want to understand and be able to code an MCMC algorithm using both Gibbs sampling like we did last week and Metropolis-Hastings like we'll talk about today. And we want to appreciate different methods that can be used within MCMC algorithms to make draws from the posterior distribution. So Gibbs sampling, Metropolis sampling, and Metropolis-Hastings sampling. Burn-in and convergence are something we always hear in Bayesian methods. What are those and why are they important? And then being able to write full conditional distributions is important for writing your own MCMC samplers. 5 learning outcomes. All right, we talked about this a couple of weeks ago, what the posterior distribution is, actually what each component of Bayes' theorem is. So when we write out Bayes' theorem, let's see, I don't have it here, but the probability of parameters given the data equals the probability of the data given the parameters times the prior on the parameters divided by the marginal distribution of the data. Here are each of those components. On the left-hand side, we have the posterior distribution. And again, the posterior distribution is a combination of the prior, the likelihood, and then scaled using the marginal distribution of the data after the data have been observed. When we have conjugate models, we saw this with, this is a binomial beta model where our likelihood is binomial and our prior for our unknown parameter phi here is beta. We can work out exactly what the posterior distribution of phi given our data is. And we did this on pencil and paper, and we found that our posterior distribution of phi given y is a beta distribution, and we have a slight adjustment of what the parameters are. So we had our our previous prior for phi, our previous prior for phi, our previous, our prior distribution of phi included a shape and a rate parameter, alpha and beta. But then when we do all the algebra, we figure out that actually the posterior distribution is a new beta distribution with this shape and this rate. Now, when we have conjugate models, this all works out really nicely as long as we do the algebra correctly. But when we have more complex models, like most ecological models, in fact, then it turns out that there is not going to be an analytical solution for non-conjugate models. And this was a big roadblock up until about 1990. We couldn't fit super complex models. And it was the advent of these techniques for sampling marginal distributions that specifically MCMC that allowed this kind of second Bayesian revival, because now we were able to develop fairly complicated models, actually models more complicated that we could ever do than we could ever do using likelihood analysis, using kind of the same steps for each unknown parameter in a Bayesian framework. So when we don't have an analytical solution, we can't sample directly from the posterior distribution using Gibbs sampling. So Gibbs sampling is what we did last week when we know what the posterior distribution is and we sample directly from that. So last week was all about Gibbs sampling, but when we have non-conjugate models, we have to use either Metropolis sampling or Metropolis-Hastings sampling, and there's just a slight difference in those two. All right, so what are we doing in MCMC? Recall the posterior distribution is proportional to the joint distribution. So we have, after we observe the data, in Bayes' theorem, there's underneath the right-hand side here, we have divided by the marginal distribution of the data. After we observe the data, that marginal distribution is fixed. It's no longer a probability distribution. It's fixed at the data that we actually observed. And therefore it's constant, and that's why we have this proportionality here. So then this becomes constant, and it's no longer a function of theta, and we can use that. All right, we have the likelihood and we have the posterior. When we sample from the likelihood, or when we develop likelihood profiles, they're not normalized. The normalizing constant, that denominator y, is not incorporated in this. We need to figure out a method to get that incorporated. All right, so let me go through these 4 bullet points here. The posterior distribution is unknown, but the likelihood is known as a likelihood profile, and we know the priors. So when we have models like this is what we're talking about. When we have a distribution that looks like this, where there's no analytical solution, there are some things we do know. The posterior distribution is unknown, but the likelihood is known. We have a likelihood profile, and we know the priors. We want to accumulate many, many values that represent random samples that are proportionate to their density in the marginal posterior distribution. Remember, marginal posterior distribution is just the distribution of one parameter conditional on everything else. What we're doing in MCMC is we generate these samples using the likelihood and the priors, and we're going to do kind of a guess and check. So MCMC is essentially a guess and check method. We're going to propose some certain values, and we're going to see how well those values work given our data and our prior information. We're going to propose them in a special way, and we're going to guess them in a special way, and we're going to check them in a special way. And after we do this guessing and checking, we're going to use these samples, these proposals, to describe the posterior distribution. And we can provide the entire posterior distribution in our reports, or we can provide means at 95% credible intervals, medians, variances, etc. All right, the marginal posterior distribution of each unobserved quantity is approximated by samples accumulated in our MCMC, our Markov chain Monte Carlo. We are sampling values of theta. Once we sample these, we can normalize them. But we have to sample them in a very special way. This is what our output from our MCMC looks like. But what we're going to do is just divide these by how many MCMC chains we have. I still haven't talked about why MCMC works or why we can get rid of that denominator in Bayes' theorem. We'll get to that in a second. All right, this is the basic steps for Metropolis Hastings. We are going to first choose a value of our unknown parameter. When I say choose a value of our unknown parameter, what I mean is we're going to propose our algorithm a certain value, and this value can be anything. So we could just choose randomly what theta star is. This is our unknown quantity we want to estimate. So this could be like a mean, an intercept, or a slope in linear regression model. We're going to say, what about this value? And then we're going to check it. We're going to check it using our likelihood and our prior, actually our log likelihood and the log density of our prior. We're going to compare it to another value. We're going to see which one's better, and we're going to keep the better one with a little bit of random variation in there. And we're going to do this over and over and over again. So in this box here, this represents the iteration number. So this is an oversimplification of our iteration number. So in our MCMC, we do lots of iterations, maybe 10,000 iterations. We propose a value of theta on our first value. We keep this with some probability that's determined by our data and our prior. And then we move on to the next step. Okay. And what we're going to be doing in deciding which one we're going to keep is we're going to keep the more probable members of the posterior distribution by comparing a proposal value, the value that we're guessing, with the current value that we guessed last time. And if we propose a value that's more probable than our last value, we're going to keep the new value and get rid of the old value. Okay. I may come back to these in a moment. I first want to get to why we can get rid of the denominator here. All right. Let's say we're doing simple linear regression like we did last week, and we're trying to estimate mu, the intercept of this model. Recall last time we had to choose a starting value for mu. We had to set that initial value, and it didn't matter where we started because the support of mu was negative infinity to infinity. As long as we're within the support of our distribution for our parameter, then it doesn't matter what our starting value is. We start out with the starting value mu. Now, suppose we don't know the analytical form of the full conditional distribution for mu. That is, we can't work it out by paper and pencil. What we can do is say, let's look at mu and see what the probability of our data given that value of mu is. So we could do something here like d norm. What's the probability of observing the data we saw if we had this value of mu that we proposed or we chose as our starting value? We can multiply that by the probability of mu based on what our prior distribution is. And actually what we do is we just take the log in each one of these functions and we add them together. And that's going to give us this top part here. All right, so that's one proposal of mu. Now, on our next iteration in our MCMC chain, we're going to propose a new value of mu, and we're going to call this mu star. So our MCMC iteration is k plus 1, or if it's only our second iteration, it would be 2. And then with this new value of mu star, we're going to do the exact same thing. We're going to calculate the probability of observing the data we saw, given this new value of mu star. We're going to multiply that by the prior of mu star. And then the critical step here is we're just going to calculate the ratio of our new proposal versus our old proposal. So we divide this by this. And if we divide this whole function here by this function, what's going to happen? And this is the key step in why this works and deals with our problem in the denominator. So let's take a minute to think about that. And while you're thinking about that, I'm going to code up some R script just to show exactly in kind of in slow motion what is going on with our Metropolis Hastings. Okay, any idea what's going on here? What happens to that denominator?
Hey Perry, you're dividing the top equation by the middle equation, right?
That's right.
So would that cancel the denominator out then?
Right. Yeah, the denominator is exactly the same because our data has been observed. So when we take the ratio of our proposed value here to our previous value, the denominators cancel each other out. It's that divided by that. So then we obviate the need to calculate the marginal distribution of the data. And we can compare this ratio of this proposed value to our previous value. And that's how we get this clever idea behind Metropolis updates. We can calculate the numerator here. We can't always calculate the denominator. And if we take the ratio of these two values, then the denominator cancels and we don't need to take it. We don't need to calculate it. So let's look exactly at what this Metropolis Hastings algorithm is doing in R. All right, so I'm just going to simulate some simple data here. I'm going to say theta truth. I'm going to use theta because that's what the slides say. So I want to stay consistent with the slides. We're going to say the true value of theta is 5. And we're simulating some data from a normal distribution. We're just simulating 10 values, 10 data points with a known mean and then standard deviation equal to 1. So our data look like this. You can look at a histogram of our data. We've got a couple fours, values between 3 and 4, values between 4 and 5, and so on. All right, so we have our data and we're gonna write a model. We're gonna use a linear regression model and we're trying to estimate the mean of this parameter. We're trying to estimate theta, pretend we don't know what the truth is. So let's say the priors for the theta that we're estimating, mu0 and s0 are 0, and the standard deviation is 100. So, okay, we have a model. Our model looks like, let me write this out, just so we're on the same page of what model we're trying to estimate. We're doing just a linear regression model where we have our data come from a normal distribution with mean, we're using theta here, and known variance sigma squared. And we're saying the prior on theta is normal with mean 0 and variance 100 squared. So we're trying to estimate theta. And we're going to use Metropolis Hastings to do that. Well, we're going to choose a value of theta using our MCMC. We'll call it theta 1. And we're going to say this equals 5. And then to calculate this, the numerator and Bayes' theorem of this, we will calculate this. Probability of y given theta equals 5 times the probability at theta equals 5 from our prior. To code this in R for this model, because this is normal and this is normal, we can say dnorm 5 I'm sorry, dnorm our data, the probability of our data given theta equals 5 and sigma squared equals 1 multiplied by dnorm theta equals 5. This is our prior, so our mean is 0. Our standard deviation is 100. Recall, if we take the log of these, we're still going to get the same answer, but then we can just add them up. So in R, instead of multiplying, a much more computational stable way to do that is to add them using the log. So we still use d norm. The probability of our data given theta equals 5 and sigma squared equals 1. Log equals true plus d norm theta equals 5. The mean is 0 and the standard deviation is 100. So let's just code this in R. First, we'll say we'll start off at 5, our starting value. We're cheating here because our starting value is exactly equal to the true value, but this doesn't have to be 5. We could say 50. And then we calculate the likelihood of our data given theta 1 equals 50. So this is the part of Bayes' theorem that is influenced by the data. Here's the part of Bayes' theorem that's influenced by the prior. And we add those two together. And we'll just call this MH2. All right, so we calculated MH2 for our first proposal of theta. This is our guess and check part right here. We're guessing that theta equals 50. This is part of our check part, MH2. All right, so let's go back to our slides and show what we just did. We calculated this equation here for theta k equals 1, our first iteration. We added the likelihood, the log likelihood, and the log of our prior together for one value of theta. Now what we're going to do is propose a new value of theta, calculate this here, and then divide the second quantity we get by that first quantity we get. So our first proposal for theta was 50. Our next proposal, let's say, is 45. So we'll go down here. We'll say instead of 50, let's try 45. And we'll call this theta 2. Now we can, let me change this out to theta 2. Everything else stays the same. And we calculate MH1. So now we have MH2, which we calculated first, and MH1, which we calculated second. MH2 is associated with theta equals 50. MH2 is associated with theta equals 45, and we want to see what is better. What's better, the value of 45 or 50? So we're going to divide MH1 and MH2. And calculate our Metropolis-Hastings ratio. MH stands for Metropolis-Hastings. We want our new value divided by our old value. So that's why I labeled this MH1 and this MH2. MH1 is going to go on top of our old value. Any questions so far? Now there's a slight issue with this, the way it is now, and that is each of our MH values gives us lots of numbers. It gives us one number for every data point we have. And what we want to do is just have one single number to divide that we can compare for our thetas. So when we worked out the likelihood of lots of data, we had that product symbol, the product of all the likelihoods. That recall that from a couple of weeks ago, where if we have lots of data points, if we assume they're conditionally independent, we can take the product of them. If we take the log of them, we can just add them together. So I can simply sum these up for the data. I'm not going to sum up the likelihood in here, the prior in here, just the data. And then that'll give me one number for MH1 and one number for MH2. Just on intuition from the way this problem is set up, which value of theta do you think is better? $50 or $45? So it's another way of asking that question is, what would be a better mean for this data? 50 or 45? And neither of them will be perfect at this point, but one's going to be better than the other.
Is it 45 because it's closer to our true value?
Yeah, exactly. We simulated this data with a mean of 5. And our first value is 50, our second is 45. Now 45 should be better than 50 because it's closer to the mean, unless something really weird happened when we were simulating the data. So let's just look at MH1 and MH2 and see which one is better. So MH2 is bigger. Let's see, MH2 is smaller. So the likelihood for MH1 is better. Now we're dealing in log scales here. So these numbers are more difficult to interpret. One thing we can do to get out of these, because we took the logs in each one of these addition terms here, we have log equals true, log equals true. We can get out of that by exponentiating this. And when we exponentiate something that's divided, we can change that to subtracted. Yeah, so that's huge. It's a huge difference. So MH1 is this, because this is so big, it's saying MH1 is much better than MH2. Meaning 45 is a much better choice than 50. It's infinitely better. Okay, I'll do the next step on this too. I'll propose another value and we can check that. But any questions about this so far? Okay, I'm going to go back a couple slides, the ones that I glossed over before, and revisit those. So the process in MCMC is we propose a value for theta. Our first value, we had to choose, and we called this a starting value. We chose 50 for our first value of theta. Then we calculate the probability of theta given, probability of our data given theta, and the probability of this proposed value from our prior. And then we propose a new value for theta. In our example, on our studio, we chose 45. Now we calculate the probability that theta, our second proposal, is greater than the probability of our first value. So it's our guess and then our check. And here's our check, the probability that our second value is better than our first value. If it's better, we're going to say theta 2 from our MCMC equals our second value that we chose. So because 45, the probability of 45 was much bigger than the probability of 50, we're going to say our second value in our MCMC chain equals 45. And we're going to throw out our first value, which was 50. So we stored 50 here. Then we chose 45. We calculated the probability that 45 was better than 50. And because it was much better, we say our second value equals 45. And we then go on and repeat this. So now we're going to propose a new value. It could be 40, or it could be 45, or it could be 50. It could be any number in there. We're going to propose a new value. We're going to calculate the probability that our new value is better than our old value. If that probability of our new value is better, this says it's not better, but if it is better, we're going to keep the new value. But if the probability of our old value, like it says here, is better than our new proposal, we're going to say in our MCMC chain that the third value of theta equals the last value. So we keep proposing new ideas, new values for theta. If they're better than the last value, we're going to say, okay, let's go with that. But if we propose a value that's worse than our last value, we're going to throw that out and keep our last value. Let's go through a couple more iterations in R to show a couple different scenarios. All right, so our starting value is 50. We calculated the numerator of Bayes' theorem here. The only nuance here is we took the log so we could add them together. We get a value for MH2. Now we propose a new value. We're proposing 45. So this is our first proposal, but our second value in our MCMC. We calculate MH1. We figure out the difference between our new value, how much more probable our new value is compared to our old value. It's infinitely better. So we're going to say, let's call this theta save 1 equals theta 2, because that's the one that was better. I first have to create theta.save. So this is what we created last week in our Gibbs loop when we said bookkeeping. All right, so we're saving theta 2 because it was better. Now let's propose our third value. And this time I'm just going to call it theta star. And let's say theta star equals 46. We know what the true value is, so we know this one shouldn't be better. The true value is 5, and 46 is further away than 45. But anyway, let's see what the data tells us. So we'll call this MH1 again. Here's our new value of theta that we're proposing. We need our old value as well. Let's see, our old value was called theta 2. We can keep this the way it is. We have this comparison here. And we see that this is almost 0. So there's basically zero probability that our proposed value, theta star, is better than our last value. Okay, since there's zero probability, let's say theta equals theta 2, and we'll start another value. Let's propose a new value, theta dot star. Let's say 40, our last value is 45, let's say 44. And I'm just going to copy and paste this down here. So our new proposal, theta star is 44. We can calculate MH1 again. Now, I said up here that theta equals theta 2. I'm just going to delete this theta 2 here. And let's see if this value, this proposal value, theta star, is better than our last value of theta. And it should be because it's closer to 5. We know that because we chose the mean. And it's huge. So there's almost, again, infinite probability that our new value is better than our last value. All right, let's just keep going. Well, because that's huge, we're going to say theta equals theta star. So we're resetting theta. So here we said it wasn't better. When we calculated theta star equals 46, the probability that 46 was better than 45 was almost 0. So we said theta equals our last value. And then we're going to store that. Now we're proposing 44. This is almost infinitely better than our last value. And we're going to say theta equals, instead of just saying theta like last time when it wasn't better, now it is better. We're saying theta equals theta star. Okay. And we're going to keep doing this over and over again. 44, let's say 39, what it was last time was 44, so let's do 43.999. Just a guess. Calculate MH1, calculate MH2, and we see that the probability that this is, our new value is better, is greater than 1. So we're going to keep our new value. And we know that probabilities can't be greater than 1. So let me just put in a condition here. I'll just say the minimum of this or 1. So that way, if this is greater than 1, we just get a 1 back. So we got 1. So our new value is better with probability 1. So we're going to keep our new value. And I forgot to save this down here. Okay. So we can just keep doing this. I'm not going to write this out 10,000 times. So instead, let's put this in a for loop, right? So let's say for k in 1 to 10,000, I'm going to call this MH. And because I can't check this every time, I'm going to just put a statement in here that says if MH is greater than something, then I'll keep the new value and I'll get rid of the old value. But if MH is less than something, I'll keep the old value and get rid of the new value. So if MH is greater than, let's just do a uniform distribution between 0 and 1. Then, oops. I will say theta equals theta star. And if the new value theta star is not better than the last value theta, meaning MH is not bigger than this uniform distribution, then it's just going to skip this entire step and theta is going to stay what it was. And it's just going to pretend like theta star never existed. And I can save this. In the kth spot, whatever theta is. All right, let me walk through this one more time before we run it. We're going to have to choose a new value of theta for each iteration. I was choosing these by hand last time just to demonstrate what's going on. But let's add some randomness to this. Let's just do a random walk, simple random walk. The way we do that is we're just going to sample one value randomly, and we'll use as the mean the value we had last. And then the standard deviation is going to tell us how far away each new proposed value is going to be from the last value. And this is called a tuning parameter. So let's just say 0.01. Let me put a couple more zeros. Okay, so we're going to sample a new value of theta, propose a new value of theta using a random walk. Our new value here is 44.00001. We're going to calculate MH1 of our new value, MH2 of our old value. MH is our metropolis Hastings ratio. That's going to be either this value, it's going to be the difference between MH1 and MH2 in the exponent, or if that's greater than 1, it's just going to choose 1. And then it says if MH is greater than this random value here between 0 and 1, we're going to keep our proposed value. But if MH is very small, then this is going to be unlikely. This is going to be close to 0. And we're going to skip this step, and theta is just going to stay what it was last time. And then we're going to save this as our output. All right, so any questions about any of these steps? There's one thing in here I haven't explained yet, but I'll talk about that in the future.
I have a quick question, Perry. I was where do you, I know you're choosing these numbers randomly right now, but is there somewhere that normally the algorithm would start in your data if you had your data and you were doing this, and is there like a standard piece that it follows, or?
The starting value of the algorithm, the first value of theta, is that what you're talking about?
Yeah.
Yeah, that is, so I chose 50 as the very first value way up here, right? I don't know that the true value is 5. I mean, I do know, but in reality, we don't know. So I said, well, let's just choose a value, our very first value as 50. And this could be 100, it could be a million, it can be anything as long as it's in the support of theta. So these are called, you hear these called starting values in Bayesian literature. And ideally, it doesn't matter. In principle, it doesn't matter what your starting values are as long as it's in the support of the data. So a good place to start, if you're trying to choose a very good starting value, might be just whatever the mean of your data is. Oops. The mean of y. So we just took the mean of our data. We say it's 5.15. And that may have been a better place to start than 50. In theory, it doesn't matter where you start, but it just may take longer to converge if you choose poor starting values. For this simple model, it's not going to matter, and I'll show this in a plot.
So when this is running in a program where you're not actually coding it, the Mcmc will choose the starting number.
Yeah, if you're using JAGS or Stan or some other program, there's a place that you can put in a starting value. There's an argument for that. If you don't put anything in, it'll just choose something randomly.
Thanks, that sounds crazy.
Yeah, and the only difference in what you choose for starting values is how long it'll ultimately take to converge. And we'll show what I mean by converge in a second once we run this. Yeah, good question. Okay, let's see if everything's working here. Any other questions before I go ahead and run this? All right. So I'm going to run this little MCMC algorithm. It was essentially instantly, even though we did 10,000 iterations. And our parameter that we were sampling was theta. So let's plot. Before I do 10,000, I actually want to do just like 100 so we can actually see every single one instead of just a big blob. All right. All right. So we see all the different values here where we started it off at whatever our first value of theta was. And we get this random movement around here. Oh, it actually did 10,000. How did it do 10,000? I said for. Let me start up here. There we go. Okay. So there's 100 iterations of this chain. You know, some values that it proposed, even it starts to go down, then some are actually okay. It goes back up, and that's because of the random nature of this value here, what we're comparing it to. Just making sure I didn't leave any. result looks right. Okay. Let's run some more iterations. But anyway, what I was saying before was, even though the true value is 5, the chain isn't always going down directly to 5. And the reason that is because we added the stochasticity right here. We're sampling a random variable between 0 and 1. And even if this is sometimes close to 1, if this randomness we're adding to it is also close to 1, sometimes we're going to reject values of MH that support the new value instead of the old value. And we're going to move towards that. So it's not going to be a direct line to 5 like we see, but let's add some more samples here. Let's make this hasn't converged yet. We know that because we know what the true value is. All right, so after we run this a little longer, our starting value is up here, and it's starting to move down in the direction towards 5. Still hasn't gotten there yet. We're going to need more samples. And this is why choosing good starting values can save you some time, because you can omit this searching part of this algorithm where it's trying to find the best part. And it has to go a long ways. It has to go all the way down to 5, which the true value is. So let's add some more iterations. Let's do 100,000. 100,000 takes a little bit longer. And we see it's still working its way down there. It's getting closer and closer, but it's taking a while. Let's do 1 million. So now we have 1 million Mcmc chains. It's starting to take actually a considerable amount of time. We're in the tens of seconds now. And if we plot that, this plot might take a while. Still loading. Any questions while this is loading? There you go. Okay, we see it knows in general the right direction of where to go. It's just taking a long time to get there. Now there's 2 ways in this algorithm we have here that we could speed up the time it takes to actually get to where it's supposed to be. One of those is the starting value. We could say theta 1 equals 5. And it would be there. It would be in the right spot, and it would search around the right area. It wouldn't have to drop all the way to 5 first. The other option comes in what I called the tuning parameter before. So this value, when our proposal distribution, when we're proposing new values of theta star, we're choosing how we're proposing those values. And the way we're doing it right now with this very small number is we're saying, we want to choose a value that's centered around our last value, but that the standard deviation is actually very close, very small, and therefore very close to the last value. So it's not going to vary that much. Let's look at what the value of theta is right now. So right now our value of theta is 42.15174. When we sample a new value, because this tuning parameter, the standard deviation here, is really small, our new value that we propose is going to be very close to 42.15174, and in fact it's 42.15167. What if we say, well, we don't want something that is that close to our last value? That is, we can make this bigger, the standard deviation bigger, so that the proposed value next is further away. So when we do that and see what kind of proposal we have, now we're looking at a value that's different in the hundredths instead of in the 10,000ths. So this is going to give us proposals that are a little further away than the last chain is. And when we do that, it's going to allow it to search more rapidly than it did before. So let's set theta at 50 again. Start off at our original starting value. We can change these number of iterations back to 10,000. And we just changed our tuning parameter from something that was 0.0001. Let's change this just to 0.01. We run that. And I think I didn't change theta safe. I'm going to stop this. Okay, so it's still trying to print out 1,000,000 values because I didn't rerun this. All right. Let's say theta equals 50 again. Oh. One thing I'll note while we're waiting for this to catch up is the normal distribution that we're proposing values from is symmetric, meaning a value of theta +1 and a value of theta -1 are equally probable if it's centered on theta. So the normal distribution is symmetric. It looks the same on both sides. The difference between this right here is a Metropolis update, what we're doing with MH1 and MH2. The difference between a Metropolis update and a Metropolis Hastings update is that Metropolis Hastings update uses an asymmetric proposal distribution. And that causes one additional complexity, but we won't get to that today. So it's simply in what the proposal distribution is. All right, so this caught up here. I'm going to clean this up so it doesn't take up a bunch of space and rerun this at 10,000 iterations. Again, compared to what we did last time, I just made this standard deviation bigger. This is called the tuning parameter. 10,000 iterations were instant. And if we plot that, we can see it goes from way up to 50 down to 5 pretty quickly, much quicker than it did before. We might need more iterations here, or maybe we can even make this a little smaller, or bigger, I mean. Run that. And we see that with our bigger tuning parameter here, it moves through the space much quicker. It gets down to the true value, and then once it's at the true value, it stays centered around there. It converges. So that's convergence. We can plot what the true value is that we use to simulate the data. Okay. Let me do 100,000 iterations. Pretty quick. Okay, and there's the true value. So the true value is within our 95% confidence interval. We can check that by looking at the quantile of theta.save, a 95% credible interval. And so the 95% credible interval is between 488 and 6.13. So 5 is in our 95% credible interval. And if we were to repeat the simulation a large number of times, we could kind of use those frequentist ideas to say, well, the true value should be in between here 95% of the time. All right, let me set theta equal to 50 again. And I'm going to change this back to this tuning parameter back to 0.01. Rerun this. Plot this. Oh, I didn't redo this. Okay. So we see that no matter what our starting value was for theta, it eventually converges down to the marginal posterior distribution. And if we run this enough times, it'll be centered around that true value. But when we actually summarize the posterior distribution, we want to cut off this part of the chain, our MCMC algorithm. We want to cut off the time it took to get from our starting value to the marginal posterior distribution. And this is what's called our burn-in phase. So we want to discard this burn-in phase right at about 20,000 iterations. So if we say burn-in equals 20,000, and then we want theta.save equal to theta.save burn-in to 100,000. Yep. Then we can plot this again without that burn-in phase, and we can make inference on this part of our chain. And I want to do a few more iterations here because that doesn't quite have that fuzzy caterpillar look we want. Let's make it 1,000,000. I don't want this to take 5 minutes to plot, so I'm just going to thin it out. I'm going to start at the burn-in value. I'm going to end at our last iteration, which was 1,000,000. And I'm going to take every 10th sample. So let me first see if this works right. That looks good. Now I can plot this. And cut off a bunch of it. There we go. Okay. All right. So it found what the quantiles still cover, 95% credible intervals still cover the true value, so we're still looking pretty good. It's estimating a little high than what we actually simulated the data at, but remember we only simulated 10 data points. And the mean of our data is actually 5.5, even though we simulated it from a true mean of 5. So we can see that the data is really driving our posterior distribution, even though we simulated it from 5. When we simulated that data, it simulated values that tended to be higher than the mean just by chance. And we're seeing that being recovered in our posterior distribution here. All right, so our marginal posterior distribution of data, here's our trace plots. But now we can plot actually what the density is. What our marginal posterior distribution of theta is, given our data. It looks like that. And we can use this to make our inference on our unknown value of theta. And that's it. That's MCMC. We often have more than one parameter we're trying to estimate. So we have several of these steps, one for each parameter, but we just build them up sequentially. Okay. Any questions on that? And that's what JAGs and WinBugs do behind the scene. You tell them starting values, you tell them what your model is, and it generates that little for loop for you. Stan is a program that you may have heard of that each iteration takes a lot longer, but it converges much faster. The only difference between Stan and WinBugs and JAGs is that Stan uses a very fancy proposal distribution. It doesn't just use like a random walk like we have here. It uses what's called Hamiltonian proposal. Hamiltonian Monte Carlo, yep. All right, any questions on that?
Is there any reason that you would choose Hamiltonian versus Metropolis Hastings?
Yeah, so would you choose it helps with convergence of, I'm not an expert on Hamiltonian or Stan, but my understanding of it is it helps with convergence with models that otherwise have a hard time converging. So when we had a very, let's see, we got our trace plots at the end did look like that fuzzy caterpillar looking thing, but sometimes they don't look like that. They go up and down and it has a hard time finding the right value. In cases like that, a different proposal distribution than a random walk, a Hamiltonian distribution helps more than a simpler proposal distribution. So if you have fairly complex models that don't seem to, this is what Matt Forrester was saying this the other day at Stats Chats. He was saying, yeah, I had this model that I ran it for, I don't know, 5 million iterations. It didn't converge in JAGs. And I switched to Stan. It took longer, but it actually did converge. So it helps when you are having convergence issues. There is someone in the stats department who does Hamiltonian Monte Carlo quite a bit, and he would know more about the intricacies of why a Hamiltonian would be better. That's Grant Schisler, who teaches a Bayesian class in the stats department. I have a lot of models that I've ran, and some of them have been pretty hard to, have had taken quite a while to converge. And I've never had to use a Hamiltonian proposal. Metropolis Hastings algorithms, well, Hamiltonian is a Metropolis Hastings, but simpler proposal distributions tend to work most of the time. Okay, before this lecture, who had heard of burn-in, starting values, or tuning parameters, those terms? Okay.
Not that I could define them.
Okay. Okay, so let me just review that before going back to the lecture notes quick. I am going to comment this code out a little bit. Starting value is just somewhere, the first value in the proposal that we're going to give it. We have to choose a starting value at least for our first. If we're using all Metropolis Hastings, we have to choose starting values for all our parameters. Okay. And then we begin this is called our Gibbs loop. So we begin our Gibbs loop. This is the number of iterations we choose for our MCMC. I'm going to put MCMC settings. This is our proposal. This is our tuning parameter. I'll call it theta.tune. This is our Metropolis Hastings ratio. And this tells us whether we want our old value or our new value. And here we have, we save our parameters. And then we end our Gibbs loop. So for each parameter we have in our model, we're going to need one of these sections. Now this is normal. We could have just sampled from the posterior distribution because we know what that form is. We did that last week, the A inverse B, A inverse of the normal distribution. But alternatively, we can use Metropolis Hastings for anything. When you know the analytical form of the posterior distribution, it's faster. The algorithm goes faster than when you don't. So this is slower than the program we wrote last week when we sampled from the normal distribution. And the reason why it's slower is because when we're doing Gibbs sampling, we're always going to keep the new value. when we do Metropolis Hastings, we generally shoot for keeping the new value about 40% of the time. So let's actually look at see how many times we do keep the new value in this algorithm. And I'm just going to put in one extra line here. That keeps track of this thing called accept theta, how many times we accept the value, the new value. So every time this statement is true, when we accept the new value, we're adding 1 here. And we'll just start off by saying accept theta equals 0. Oh, that should be okay, yeah. So let's look at accept theta and divide it by how many iterations we had. This will give us a ratio of how often we accepted the new value, how often we accepted our new proposal. So we accepted about 94% of the time. Now, some people have gone through and worked with efficiency and computation data scientists to figure out the optimal value of acceptance when doing MCMC. And what they found was about 40%. So what this means is we're not, because this is 95% is bigger than 40%, this isn't big enough. We want to be looking over a bigger area. So we want to make our tuning parameter bigger. So let's change this from 1/100th to 1/10th. Rerun our algorithm. Actually, I'm going to rerun these. Start off at 50 again. Rerun our algorithm. Plot it. And look at our acceptance rate. Our acceptance rate moved down from about 95% to about 90%. So it's still too high, but we see that with a smaller acceptance rate, we actually get a much better looking plot down here. It looks more like that fuzzy caterpillar down here. And that's what we're aiming for. So let's make our tuning parameter bigger yet. See if we can get to that 40% mark. So we're getting close. We're at about 57%. So the bad thing about Metropolis Hastings versus Gibbs is we have to tune it. We have to choose a value for our proposal, the standard deviation of our proposal distribution, that gives us about the appropriate acceptance rate. And this takes some guessing and checking. Let's just make this 1, run it, look at our acceptance rate, and 92% again. I can make this much bigger. Oops, what I didn't do is this. Oh, yep, forgot to zero it out again. Okay. Now we're not accepting very often. We're trying too big of values away. Our proposals are too far away from our last value. Our tuning parameter is too big. Let's change it to 5 maybe. So we have to go through until we get roughly 40%. And this takes some tinkering with. In Gibbs sampling, we don't have to do this at all. We don't have to do any tuning. Still too big. Okay, so that's close enough. All right. So now we've essentially got our sample for this model, our posterior distribution. We've got it tuned. It's around 40%. It's 36%. It looks like it's converged. We have this fuzzy caterpillar looking thing. I never talked about fuzzy caterpillars in front of someone who actually studies caterpillars. So I don't know. I don't know if that goes.
Caterpillar plots.
What's that?
I thought they were called caterpillar plots.
Oh, okay. Okay. All right. So that's it. That's our MCMC. And all we have to do for more complex models is repeat this for more parameters. The different forms of the likelihood and the prior are going to change depending on the full conditional distribution. But this is these steps. Now let me go back to the whiteboard to show how this relates to the notes. We propose new values. We test them with our Metropolis-Hastings ratio. And if our new value is better than our last value, we set it equal to that, and then we store that. And we keep doing this. We repeat for k iterations. R is what we called MH. And the nice thing about these Metropolis-Hastings updates is this quantity that's really hard to estimate is canceled out because we divide our proposal value by our previous value. All right, when do we keep the proposal? We keep the proposal when this probability, the minimum of R or MH and 1 is greater than the value we sample from a uniform distribution. Okay. Here's repeating the process that we described already. So calculate R, our Metropolis-Hastings ratio, based on the likelihoods and the priors. If we take the log of the likelihoods and add them together, and then add that to the likelihood of our prior, for each of our previous value and our proposal value, we're going to calculate the R. We're going to draw a random number U from a uniform distribution between 0 and 1. And if that Metropolis-Hastings ratio is greater than that uniform value, we keep the proposal as the next value in our chain. If it's less than this, if R is less than that uniform value, it means the proposal wasn't that good. And we're going to keep the old value. Okay, and this is an example of approximating a marginal posterior distribution and comparing that to an actual real distribution. So when we use MCMC, what we're doing is we're approximating the marginal posterior distribution. We don't know the exact form of the marginal posterior distribution like we do when things are conjugate. But we can approximate it. It's not going to be exact, but if we had an infinite number of data and an infinite number of MCMC iterations, it would be exact. And this works for multi-parameter models. As complex as we can make the models, as we can write them up, we can fit MCMC to them and everything will work. All right, here is a more complex model. We used a simple linear regression model where we knew what sigma squared was, and we were trying to estimate theta was equal to the intercept. But now here we don't know our intercept, we don't know our slope, and we don't know our standard deviation. But we know the form of the model that we wrote out. We say that the likelihood is normal. The likelihood of our data, given the parameters, is normal, and we can multiply those together. If we take the log of them, we can add them together. And we know what the priors are for each of our model. Let's see. Yeah, I'm just going to go over this slide, and then we're going to end here and probably start up with this on Wednesday. All right, so we know we can set our priors for beta 0, beta 1 to be normal, and then sigma squared can be a distribution that has positive support. So uniform would work with minimum equals 0 and max equal to 10. The way the MCMC works is we set starting values for beta 0, beta 1, and sigma squared. We assume all other parameters except 1 are known and constant. So we are going to, when we choose our starting values on our first MCMC iteration, we're going to sample beta 0 first. We're going to use the values we used as our starting values for beta 1 and sigma squared and treat those as known and constant. And when those are known and constant, we can make a draw. We can use our Metropolis-Hastings algorithm to sample beta 0. We're going to store that draw, and then we're going to go down to the next parameter, beta 1. Now we're going to assume beta 0 is known. It's the value we just sampled. We're going to assume sigma squared is known, and then we're going to sample beta 1. And then for our final parameter, we're going to assume beta 0 is our sample from right above it. Beta 1 is our sample from the previous step. And then we're going to sample sigma squared and store that. And we're just going to repeat this. Okay. Let's pick up here next time. Yeah, this is a good place to start and a good place to pick up as an introductory slide next time, slide 25. What I can do now is go through an example of this model right here, if that would be helpful. Or if you're burnt out, we can end here too. I'll leave it up to you.
Can I just ask a quick question, Perry?
Yeah, go ahead.
I was wondering if, like when we first started this prior example, we didn't see it converge until we did enough iterations to get down towards the mean. But what are, I guess, some other reasons it wouldn't converge? And like, when would we be able to notice? Would it be we took this many iterations and?
Yeah, convergence diagnostics. That's a important topic in any time we fit in these models. So let's look through, let's see if we can get this to fail. All right, let's go back to this example. Let's just do, let's say our sample size is 1. I actually still think this will probably converge. It'll converge to whatever the datum is. All right, so now we just have one data point. And we tried to fit this MCMC. So we have prior information, and we have one observation, n equals 1. Let's see what the MCMC plot looks like. What was our data? No, that wasn't one. What happened? Oh, I didn't change this. Still got it. Y equals 5.3. Okay, even when we have one data point, it still converges. Let's see. Model that doesn't converge. When something doesn't converge, I'll first talk about when it doesn't, and then I'll try and show a plot of what it looks like. Something doesn't converge when there are, remember we talked about this idea of unidentifiability. It was where you have one equation and two unknowns. You can't figure out both the unknowns. It's like A times B equals 9. A could be 3 and B could be 3, or A could be 4.5 and B could equal 2. We don't know exactly what they are without a little more information. And when we see that, when we have that, that's when we'll see models that don't converge. What it looks like is essentially they look like random walks. So if I just plot a random, if I run this and just do a random walk by crossing out a bunch of this stuff. So I'm going to say theta equals theta starts random walk and then theta equals theta. So I'm just setting theta equal to a random walk. And I'll show what that looks like. It looks on the lines, they look along the lines of something like this when parameters don't converge. And it doesn't matter how many iterations I run this, let's do 1,000,000. It's always going to look like this. It's never going to get better. I'm going to thin this out before I plot it. So now I did 1,000,000 iterations. It's just going to keep looking like this random walk, no matter what I do. So this one is not converging. If we had a trace plot that looked like this, it wasn't converged. Then we have to start thinking about our model and are all the parameters identifiable? You see that a lot when we have models that have a lot of like logit link functions in them. So if you do one logit link function, everything works out pretty well. But when you start to add more and more logit link functions, it takes things longer and longer to converge. And it's because the way that transformation works, there's not a lot of information that's transferred over. Maybe at some point we'll see a model like that. But anyway, you want to get that fuzzy caterpillar look. The other thing people do to make sure it has converged to the right area is they try lots of different starting values. So they may run this 3 times with 3 different starting values and see if they all go back to the same spot. So we chose 50 here. What if we did -50? Is it still going to go to that 5 area? Let's see. Even though we started way down at -50, it still goes back up to where the true value was that we simulated it. And that's one diagnostic to make sure things have converged to the right area. They call this using multiple chains in your MCMC. And you often see plots that look like, let's call this data save. Let's change this to data save 2. And yeah, we'll start this at -100. So now I have both of those chains stored here. The first one was the black one where it started at 50 and the second one started at -100. We see they both converge to the same spot. No matter what our starting value is, they should converge to the same spot. Any other questions? If not, I can finish this out and add some more complexity to it. I could probably do that in 9 minutes for the full linear regression model. Why don't I just do that? All right, we have, let's say this is beta 0. Beta 1 dot truth is -2. And then sigma dot truth equals 10, 7. I'm just going to create a random covariate. Let's say binomial. So here's our covariate. This could be like whether or not it was forested, or whether or not it was a treatment or a control. 0 for a control, 1 for a treatment. And then beta 1 is how different the treatment versus control is. So now we can calculate the mean. And we have our data. So all we know is X and Y, and we're pretending we don't know anything else. We went out and collected data on a treatment and a control, and we measured the response variable Y. And we're going to try and see if we can figure out what these really are. So these are the processes behind nature that we're trying to figure out, that we're going to make inference on, if our experiment actually has an effect. So we know X and Y. Let's use the same priors for beta 0 and beta 1. So our priors for beta 0 and beta 1, we'll assume those are normal. But we also need priors for sigma squared, or sigma. And let's use inverse gamma with shape equal to 1 and rate equal to 1. All right, not only are we going to have to store beta 0, we're going to have to store beta 1 and sigma 2. Or I'll just say sigma. We have to choose starting values for all of our parameters. In principle, it doesn't matter what they are as long as they're in the support. So for example, we couldn't choose a negative value for our standard deviation. That would give us an error. All right, we need tuning parameters for each of our parameters. And then we need something that looks like this for each parameter. So we have beta 0, beta 1, and sigma. I'm going to quickly replace theta with beta 0. All right. So with beta 0, it's very similar. We sample beta 0. We propose a value for beta 0. Now, our mean for y is mu. So we have to take beta 0 and plug it into mu. So if we take our equation up here where we simulated the data, plug it in here, except change dot truth, because we don't know what truth is. We'll change this to mu dot star. And this is going to be our proposed value for beta 0. But beta 1, this is where we treat things as fixed. We're treating beta 1 here as fixed, and it's going to be fixed at our proposal value for the first MCMC iteration. Now we have the only thing different about mu and mu dot star is that beta 0 has been switched. So in our initial values, we also need a mu. Where's my starting values? Starting values here. I need to plug these into mu. Okay, so I'm changing beta 0, and then I have to change the expected value mu because that depends on the new value of beta 0. And then in my Metropolis Hastings update, I have mu dot star here and beta dot 0 star here. But here I have the original mu, and this stuff's all the same. The only difference here is I changed beta 0 star in this linear function. I changed this intercept. The slope is still the same. We're treating that as fixed. The only difference between mu and mu dot star, which is the only difference between MH1 and MH2, is we changed the intercept. So we're going to change the intercept, recalculate the line, and then calculate which one's better for the data based on the likelihood and the prior. Now we're going to do the exact same thing for beta 1. So after we calculate what beta 0 is, we're going to recalculate what mu is, but this time we're going to treat beta 0 as fixed and change beta 1 to beta 1 dot star and recalculate mu dot star. We calculate the Metropolis Hastings ratio, if the new slope is better than the old slope, MH1 is going to be better. If that's the case, we're going to change beta 1 to beta 1 dot star, and we're going to change mu to mu dot star. Okay. Beta 0 and beta 1 are both very similar because they're both have normal priors. Sigma squared is different. We got 2 minutes. I'm just going to work through this, and I think I'm going to have to continue explaining this on Wednesday. All right, so theta star has to be positive. If it's not, we're going to get an error. I mean, not theta star, sigma star. I know some people have to leave now. I'm just going to stop here. And we'll start off here, finishing up this Metropolis Hastings on Wednesday. I'm happy to stick around if you have any questions, so.
Thanks, Perry.
You're welcome.
Yep, thank you.